Although many people don't think of spheres as important as cylindrical containers, they actually have a lot of use, such as reactors and storage tanks. For example, they're used to hold liquid nitrogen. They're also valued as pressure vessels. However, even though they're able to hold sometimes twice the internal pressure as something cylindrical, they're much more expensive, which makes them a little less practical. Design of these spherical containers involves knowledge of material science coupled with heat transfer. So in this screencast, we'll address the heat transfer part. So what we'll do is look how to analyze conduction through a spherical wall that is one-dimensional, steady state with no heat generation. So we start with Fourier's law. So that states that the heat transfer rate in the radial direction is equal to minus K, which is the thermal conductivity, times A, which is the area normal to the heat transfer, dt dr. And for our sphere, this is equal to minus K times 4 pi r squared dt dr. We assume that the thermal conductivity K is constant and that Q sub R is independent of R, and we can integrate both sides. So we're going to need boundary conditions such that T is equal to TS1 at R equals R1, and T is equal to TS2 at R equals R2. We end up with an expression QR, or Q sub R, is 4 pi times K, the thermal conductivity, TS1 minus TS2, and this is all divided by 1 over R1 minus 1 over R2. And so what we're looking at is a shell like this, where our R is always measured from the middle, R equals 0. And so here's our R1, and here's our R2. We can also write this in terms of a resistance, such that Q sub R is delta T divided by the sum of the resistances that right now we're calling conductive resistances between those two temperatures. So our conductive resistance is going to equal 1 divided by 4 pi K, and this is all multiplied by 1 over R1 minus 1 over R2. However, spherical containers often have more than one material, especially if insulation is needed. So let's look at a more complicated situation where we have more than one shell with different materials. So if we say that this material has a thermal conductivity K1, this K2, and this K3, and we measure our radius. So here's our R1, R2, R3, and all the way to the outside, which is R4. So let's set this up as a thermal circuit, starting with the surface at R1. So we have our TS1, which is that temperature. And the first thermal resistance it runs into is 1 over 4 pi K1 multiplied by 1 over R1 minus 1 over R2. Next, here's the temperature at the surface of 2. And this resistance is 1 over 4 pi. Now we have K2 multiplied by 1 over R2 minus 1 over R3. And we're going to continue to do this thermal circuit until we get to the outside, or TS4. Note that we haven't considered any convection, which could be occurring both in the center of the sphere as well as the outside. And if we did that, we would have to add to the left side. So here's our bulk temperature, and the resistance would be a convective resistance. So this is our 1 over our thermal convective coefficient times 4 pi R1 squared. And then we go to TS1, continue the circuit all the way down to the end until we get to TS4. And now we add to that our convective resistance for the outside, which is 1H outside, the convective heat transfer coefficient, times 4 pi R4 squared. And then we have our bulk temperature. So now when we find our QR, and let's assume that we have not only the conduction but the convection as part of our system, it's going to be our first T infinity minus our last one divided by the sum of the thermal resistances in between them, which include 2 convective ones and 3 conductive ones. In another screencast, I'll show you how to use this analysis in an example problem.